Okay, now we'll start computation in memory. This is kind of the sub-agenda. When I give a talk on computation in memory, I actually go through all of this, but we've covered a bunch of this due to the way we approach this tutorial. Basically, we talk about major trends, and I've already motivated intelligent memory controllers from the bottom-up perspective. Essentially, today, we have a huge push from the circuits and devices that, in my opinion, requires intelligent memory controllers to solve the difficult problems that we're having at the circuit and device levels. To solve the row hammer problem, to fix the refresh problem, for example, to enable hybrid memories, to enable quality of service. All of those require us to make memory controllers more intelligent, to add more computation, add more capabilities into the memory controller. I'm going to motivate from the top down also the same fact. We want more intelligence in the memory controllers, more functionality in the memory controllers to accomplish more for applications and systems, basically. And hopefully I will convince you that we're kind of squeezed in the middle today. Circuits and devices, all of the scaling issues are pushing us to make the memory controllers intelligent. Applications want intelligent memory controllers. Essentially, we want computation capability in the memory controllers because that will enable a lot of benefits. Processing in memory is actually not an old idea, not a new idea. It's a very old idea. In the general purpose domain, it was proposed in the late 1960s. The first paper on it is by Harold Stone in IEEE Transactions on Computers in 1970. It's called A Logic in Memory Computer. It's a beautiful paper to read, actually. And then later, many papers were written on the topic. It never materialized really well in the general purpose domain, at least. Even in the special purpose domain, not easily, for many reasons, which we may get into. But I think one of the reasons was the fact that we were never squeezed as much in the middle. Yes?
Technology also. Memory technology and processor technology not the same.
Exactly. I'm going to talk about that also, actually. Right now, the technology is actually making things a bit easier with 3D stacking, for example, logic and memory. Maybe with different thinking about DRAM, because we're having so many difficulties in DRAM that maybe there are other ways of using DRAM as opposed to just improving capacity, right? Okay, and then I'm going to talk about two different directions in memory, processing in memory, and then talk about adoption issues. Maybe average Joe will be a concern over here a little bit. Programmer Joe, I guess. Not the average Joe who's not a programmer. We don't care about them as much in terms of processing in memory. Hopefully they will use processing in memory, but they will not program it. And then we'll conclude. Okay, so let's start with this pull from systems and applications. So if you look at systems and applications, there are three major trends. And I think these are kind of obvious. I'm going to give you examples of it again. But data access is a major bottleneck. Applications are increasing the data hungry. I've already given you genomics as an example. But if you look at any interesting domain, data is growing. Energy consumption is clearly a big limiter in many systems today, and data movement energy dominates compute. I've already given you examples. Let's go through this a little bit more. Essentially, the observation is that the high latency and high energy that we have today in systems is caused by data movement. We have long energy-hungry interconnects, energy-hungry electrical interfaces, and movement of large amounts of data in the system. And the opportunity, we can minimize this data movement by performing computation directly inside or near where the data resides. And that's the idea of processing in memory. Of course, I don't want to be a purist in this case about what it means to be processed in memory. I'm going to use these terms interchangeably somewhat. Basically, processing near data, processing in memory. To me, all of them is the same. You're doing processing outside the computation unit today, close to where data is. Of course, the closer you get to data, the less you move the data, you will get bigger benefits. If you do the computation inside the memory cell without moving the data, that could actually buy you a lot of benefit, of course, right? But I'm going to use these interchangeably over here. And the general concept is applicable to many storage and movement units like caches, SSDs, main memory, network, and controllers. And I think all of them are interesting. The focus will be on main memory in this particular lecture. So basically, I'm going to pose this as an energy efficiency problem, but it's going to help us improve latency, performance, and I believe security as well. If you can actually do processing inside the memory, you may actually add security functions inside memory, and that could actually enable a more secure system going forward. We've actually been looking at this. I don't have time to talk about it, I think. in this particular tutorial, but we, for example, shown that you could generate two random numbers inside the DRAM itself. You could clear the data inside the DRAM if you put the right functions inside the DRAM very quickly. This could prevent different types of attacks. You could have physical unclonable functions inside the DRAM, and I believe you could have other security functions inside the DRAM by building in security primitives. And maybe you can solve a lot of the issues that we're having with CPUs in terms of security, because a lot of the issues that we're having with CPUs in terms of security are because of data movement also. Okay, so let me go back to this picture and deconstruct what I said earlier. I said reliability and security is the most important problem, right, for humans. But that's not actually true. I mean, that's not what Maslow said. It's really about physiological needs over here. Basically, we really need energy to survive. If you don't have energy to survive, who cares about your reliability and security, right? It's a second-order concern compared to survival, I think. Of course, security can be survival also, but if you don't have energy, maybe you don't care about the outside threats. So in my opinion, the question that we have in computing going forward is like this. Do we want a world like this, or do we want a world like this? I'd prefer the former one, I think. But of course, we don't want a world like this doing nothing, right? We still want high performance. We want to solve important problems. So we want sustainability and energy efficiency and high performance together. This high performance, but not sustainable, perhaps. Right? So how do we get all of these at the same time? Oh, I don't know why this is here, sorry. That's going to come later. I should fix that later on. Okay, so the problem is, today we have a data access problem. It's a major performance and energy bottleneck, and our current design principles cause great energy waste and also great performance loss. I put this in parentheses because we do a lot in our systems to overcome the performance loss that we have because of memory access. We add a lot of mechanisms, caches, prefetchers, many levels of caches, sophisticated policies in caches, multi-threading, many levels of multi-threading, sophisticated out-of-order execution engines, and they're there to reduce the performance loss. But they cause even more energy waste and even more complexity. Essentially, we're in a vicious cycle right now. We're really not solving the memory problem where it should really be solved. We're really trying to tolerate it somehow by building techniques that can tolerate it. There may be overcoming some of that performance loss, but clearly not all of them, because processors are still waiting for data most of their time. But they're exacerbating the energy problem. So we need to break this vicious cycle, I think, somehow. And I think it comes by acknowledging the problem first. Processing of data is performed far away from the data today. And as a result, we have this problem. So if you look at a computing system, it consists of three major components: computation units, communication units, and storage and memory. And it's clear that we've heavily optimized the computing unit today. Computing unit, in my opinion, consists of accelerators also. They're all part of the computing unit. You need to move data to accelerators before you can process it. We're overwhelmingly processor and accelerator centric today. All data is processed in the processor at great system cost, and it's heavily optimized over here. Everything else is not optimized as much. Basically, they're dumb. They cannot do anything to the data. You need to move the data to the computing unit before you can compute. Yet we know very well that memory is the big problem. I've already given you the story of the excites showing that the alpha processor operating at 1/18th of its peak bandwidth, right? This is data from my own PhD thesis. This is where it should really appear. It should have appeared actually after this particular quote. This is the quote that Dick Seitz had in his 1996 paper. He says that, "I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors." Now maybe that's too strong, but I think this really hits the point right. Of course, this is my PhD thesis, so I have to put it over there if you're interested in looking at that. Okay, this is something that I didn't show. So if you don't believe any of that, since everybody believes Google, I had to provide data points from Google. This is Google's ISCA 2015 paper. It's a nice paper that analyzes their data center workloads. And it shows essentially the same thing. Basically, according to Google, this is their old data center workloads. You can see Gmail, indexing, search, video, ... And they basically show that a state-of-the-art microprocessor is most of the time waiting for data to come back from memory. Most of the time it's doing nothing, essentially. Only 10 to 20% of its time it's finishing instructions. And you can read the paper for more analysis. They analyze the problem a lot more. Basically, you can see that the processor is stalled waiting for the cache, meaning the memory subsystem, most of the time. Basically, we have a processor-centric design the reason we're seeing all of this is we have a grossly imbalanced system. Processing is done in only one place. Everything else just stores and moves data. As a result, data moves a lot. And because the latencies are long and we don't have enough bandwidth and we have a bottleneck, processors are just waiting for data to come back. And this is energy inefficient because data moves a lot. Low performance because clearly we're not doing a lot of computation all the time. And this is complex also because we're adding a lot of complexity. And this leads to overly complex and bloated processor and accelerators. As I mentioned, we have complex hierarchies and mechanisms which exacerbates energy inefficiency. We could have used those transistors for something else, potentially, right? And it's complex. As a result, we have the picture that I showed you earlier. Most of the system is dedicated to storing and moving data. If you look at a state-of-the-art microprocessor, more than 80%, more than 90% of the real estate is not doing computation. So energy perspective, I've already given you this. This is from Bill Daly. Basically, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. And if you don't believe that, there are other results that are showing that, again, a memory access is 2 orders of magnitude more energy hungry than an add operation. I've given you some examples from the recent DAC AI accelerators. It's the same thing, basically. And as a result, most of the system energy is spent on data movement. Basically, we do not want to move data. We want to keep where data is, and we want to do computation. At least we want to enable the option. We don't want to do it all the time, perhaps. Sometimes caches are very beneficial. You move data once into the cache, and you do many operations on it. And then you overcome the cost of moving the data. If you can do that, maybe caches are good. And actually, we found out that caches are good in many cases. But if you're doing random access, then you don't have that luxury. So I believe we need a paradigm shift to enable computation with minimal data movement. Compute where it makes sense to do it, where the data resides. Make computing architectures more data-centric. And again, this is not just memory. It should be enabled into caches, in the interconnect, in the memory controllers, in the main memory, in the SSDs, wherever the data resides or wherever the data is moving, wherever it makes sense. Today we have no option, basically. We have no capability to do computation somewhere else other than the processor or the accelerator. So, but we want to make the computing architectures more data-centric. So in terms of memory, essentially this is what we have. We would like to, memory can store a lot of data, a lot of applications clearly. We want to be able to query memory, and we want to be able to get results out of it. We want to be able to treat memory as a first-class citizen whom we can ask questions to, just like a processor, right? Can you execute this for me, for example? And if the memory says yes, maybe it can execute and return the results. Of course, there are many questions over here. How do we design the compute-capable memory and the controllers, the processor chip and the in-memory units, the software and the hardware interfaces to be able to do that? Today, we don't have the hardware interfaces to do this because the memory interface is very dumb, in a sense. You can do read, write, refresh, power manage a little bit, but that's it. You cannot ship functions to memory. And also software interfaces don't exist, but some distributed system-based programming models can be a good fit for doing some of these. So system software and languages, compilers may need redesign also to take advantage of it, and algorithms as well. I believe also theory. In some of the other slides I had theoretical foundations over here. If you actually think about computing theory, implicitly all of the assumptions over there is based on the fact that processor is doing the processing. It's not where the data resides that you can do processing. You need to move the data somewhere else to do the processing. But maybe if you think about processing inside the memory, theory needs to change a little bit as well. Okay, but basically we need to think across the stack a little bit. There are a lot of research problems across the stack. So I'm going to give you some examples of this, but we'll need to have a solution across the stack also. Okay, so why is it interesting today? As I mentioned, there's a huge push from technology to make the memory controllers more intelligent because DRAM scaling is very problematic. I've given you evidence from the field that we already have real errors that are slipping into the field. As a result, people are looking, and also industry is open to new memory architectures. There are controllers already close to DRAM with 3D stacked architectures, for example. This is one example of it. You have a logic layer underneath memory layers, and they're connected to each other with high bandwidth, low latency connections. And even newer examples, more monolithic 3D architectures are under development today. And there are some examples, experimental processors that can do, experimental memory chips that can do very limited forms of processing. I don't necessarily like the functions that they've added over here, but at least they can do some processing, right? Deterministic finite automaton processing inside the row buffer. Very limited, but people are experimenting with things like this. And this is industry, like real industry is experimenting with things like this. On the other hand, we have a huge pull from systems and applications. Data access is a major bottleneck. Systems are energy limited, and data movement is much more energy hungry than computation. So we're basically squeezed in the middle, I think, which requires us to think out of the box a little bit. So the question is, what do we do? As I said, this is not a new idea. People have looked at processing in memory in different ways. People have looked at a lot of associative processing, actually in the 1960s, for example, which is a very limited form of processing in memory. People have looked at putting full processors inside the DRAM chip. I don't think that's going to work very well going forward, because these are very different processes that they require. But maybe we should think a little bit out of the box and exploit either the new technology that's beneficial, like 3D stacked memory, or maybe think about what can we reuse memory to do very, very efficiently with minimal changes. Surprisingly, this has not been thought as much, so I'm going to talk about that first. How do we minimally change memory chips so that they can be treated as simple accelerators for important functions that could be very useful to the applications? And I'm going to talk about DRAM in this case, but actually the ideas that I'm going to describe are applicable to many non-volatile emerging memory technologies, and people have built on the work that I have described to do some of these functions in emerging memory technologies like phase change memory, for example, and also RRAM, memristors. They also enable some other opportunities like matrix computations inside the 3D structure. I'm not going to talk about those, but I'm going to show you some examples from DRAM. But keep in mind that I think very similar functions are applicable to other chips. Basically, DRAM has great capability to perform bulk data movement and computation internally with very small changes to its structure. We call this processing using memory a little bit also. You already have memory, you use the memory to do some processing. Basically, you can exploit internal connectivity to move data between banks, for example, or between different subarrays or between rows. Or you can exploit the analog computation capability. And maybe you can do even more. So let's see. I'm going to give you some examples out of this. I'm going to start simple, not even talk about computation, but I'm going to talk about data copy and initialization. Today we have a bunch of functions like bulk data copy. You copy one page to another page, on copy on write, for example, in systems. You initialize an entire database, for example. And to be able to do that today, you go through the processor. Processor does the copying, processor does the initialization. It writes all zeros to memory. Now the question is, does this make sense? Well, there are a lot of applications that actually use it. So whenever you're initializing a huge database, does it make sense to actually spend time, wait for everything to be written by the processor byte by byte into the entire memory that you're trying to initialize? That's one example, right? And this happens actually in operating systems. Whenever you free a page, you need to zero it so that you don't leak information from one process to somebody, right? And there are many, many other examples. And again, if you don't believe us, Google has recently provided support to what we were saying. They basically said in this paper that I also mentioned, 5% of the entire execution cycles in their data center workloads is spent on two function calls, memmove and memcopy. And these are just two sources of data movement. There are many, many other sources of data movement, clearly. They call this as part of the data center tax. And they actually cite the paper that I'm going to talk about as one of the solutions that could fix this problem. So I'm going to talk about that work. Essentially, how do we do the bulk data copy today? If you want to copy a source page to a destination page, you don't have any other option today apart from going through the processor chip. Basically, you need to bring the source page byte by byte into the caches, and the destination page byte by byte, do the write, and then flush the destination page byte by byte all the way back into memory. Essentially, you go through the processor to do this copy. This causes high latency, high bandwidth utilization on perhaps the most important bandwidth bottleneck resource, cache pollution, but you could actually eliminate that by setting up your memory controller to do this copy through the direct memory access engine. So you could bypass the caches and do the copy just through this, but you've already wasted a lot of energy going through the memory bus by doing that still. maybe you avoid some waste over here. An unwanted data moment, because maybe you're just copying the data and you're not going to reuse it anytime soon, right? So if you look at a 4 kilobyte page copy through the memory controller, not even going through the cache hierarchy, with some technology assumptions that are in the paper, it takes about 1,000 nanoseconds and 3.6 microjoules. And this is a small copy. It's only 4 kilobytes. Now, if you gave this picture to a child, maybe 10 years old, and asked the question, does it really make sense to do it over here? Is there some other solution? I believe they could be able to come out with a solution that says, okay, why don't you do it just over there, you know? Sometimes I think we should really think like a child and maybe employ solutions that will be developed by children. So wouldn't it be nice at least to have the option to tell the memory, please do it internally and don't bother anything else in the system. I'm not suggesting that we should do it always, because actually the results suggest that you should not do it always. Sometimes putting it into the cache is a good idea because you're going to reuse it immediately in the processor, assuming that it makes sense to do it in the processor again. But having this option enables a lot of performance improvements and energy improvements. So this is low latency, clearly. I'm going to show you examples of how to build it to be low latency. Low bandwidth utilization, essentially no bandwidth utilization. You just send a command to do it. No cache pollution, but you could eliminate that by doing this through the DMA engine today. And no unwanted data movement. And I'm going to show you an example that takes us 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And you could optimize this even more, actually. This is an unoptimized version. And the idea is very simple. We call it row clone. And in the best case, this is how it works. The two rows, the two pages, are in the same DRAM subarray. They're connected to the sense amplifiers over here. Essentially, the idea is to use two consecutive activates. You first activate the source row, which brings the data into the row buffer. Now the data is strong in the row buffer in the sense amplifiers. Now the idea is to send another activate command into the DRAM, which implicitly deactivates this row and connects the destination row to the row buffer, and the data that was stored in the row buffer is driven into the cells in the destination row, because sense amplifiers are very strong over here. That's the idea. By activating the source row first and then activating the destination row next, you accomplish this copy without moving the data further away from the row buffer. So you still need to move the data to the row buffer, of course, in this case, because reads are destructive in DRAM. So this is negligible hardware cost. Actually, you could almost do it in real DRAM chips. And this leads to a significant latency reduction and significant memory energy reduction, as you can see. It's more than an order of magnitude and almost 2 orders of magnitude energy reduction. Of course, you want to be more general, and we have mechanisms for doing it interbank. So if your source data is here, in this bank, and destination is somewhere here, you could use the existing shared internal data bus. With some slight modifications, you could set the source bank to read mode and destination bank to write mode and copy the data internally. Of course, you're limited by the connectivity, which is really narrow inside the shared internal bus in DRAM. It's 64 bits over here. As you widen it, you'll become better. But narrowness also helps you in the sense that you could copy only 64 bits from here to here, right? You could do very small scale copies as well. So there's a granularity issue that we need to fix. But I think we have in general, we have a problem with connectivity in the memory chips. If we really want to have better performance inside the memory chips, we need better connectivity also. So interconnects inside the memory chips are going to be more important going into the future. And I think this is also important from a nature perspective, because I think the nature is much more connected than the chips that we build today. Yes?
I don't know if you want to finish before we ask questions.
No, go ahead.
Okay. So I was wondering, how did you measure this this energy consumption? Did you build a real prototype?
No. It's very hard to build a real prototype in DRAM. So we do a lot of energy models in DRAM.
Okay.
And of course, there is inaccuracy in the models, but we actually have real DRAM chips as our basis for the power models. We release the power models also that we use.
Okay.
You can look at our Sigmetrics 2018 paper for the most recent one. It's called Vampire. We had to concoct the Vampire acronym, of course. Okay, anyway, basically this is, so this also leads to significant latency reduction and energy reduction, but it's not as much as when you have the source row and the destination row in the same subarray, of course, because you don't have the wide connectivity. So the difficulty is in when you actually want to copy from this subarray to another subarray in the same bank, but I'm not going to talk about that. Basically, the generalized row clone, if the source and destination are in the same subarray, it's 2 consecutive activations, you get the highest benefits. If they're in different banks, you get some benefit. If they're in different subarrays in the same bank, you use intra-bank copy twice. You don't get a lot of performance benefit, but you get a lot of energy benefits. But we have some other solution over here, and the solution is really increasing the connectivity. Basically, if you add more connectivity between the subarrays, you can actually move the data between the subarrays better as well. And maybe I'll talk about it when we talk about reducing latency in memory. Okay, all of this comes at very low area cost. And you can see that the benefits depend on where your source and destination rows are. But once you have this capability, maybe you can design system software and memory allocators that ensure that you get the highest benefits as much as possible. That's why this is an across the stack problem. You don't want necessarily the average programmer Joe dealing with how to get the biggest benefits. But if you design the runtime system, the memory allocator system software, to allocate a destination page to the same subarray as the source page, whenever you're doing copy on write, maybe you can get a lot of these large benefits. Okay, and this is the paper that introduced the idea. And clearly, this is not even doing computation, right? This is really just doing data copy and initialization. I didn't talk about initialization, but initialization is really a special case of copy. You initialize one row to 0, and then you copy that row to all of the rows in the subarray, for example, if you're initializing all of your memory to 0, for example. Or a particular pattern, again, it's the same thing. Okay, similarly, we can support other operations like AND, OR, NOT, and majority. I'm going to talk about that right now at low cost. And the key idea here is to use analog computation capability of DRAM, because chart sharing by nature does some computation, and we're going to exploit that. This is similar to what other people are also going to do in emerging memory technologies later on. And the idea is very simple. You activate multiple rows. Whenever you activate multiple rows share the charge, and their values determine the end result. I'm going to give you an example. And this leads to significant performance and energy improvements in these bulk bitwise operations, and NOT well, NOT doesn't get implemented this way, but I'm going to talk about NOT in a little bit. Okay, and new memory technologies, I believe, enable even more opportunities because these are fundamentally non-destructive. In DRAM, you have to move the data somewhere because whenever you read a row, you destroy the row. With new memory technologies that are non-volatile, you don't destroy the data, so you can actually do even more. I believe there's a lot more potential over here, and people are exploring this. And I think there should be more work in this area going forward as well. Okay, so let's take a look at the DRAM case. Let's assume that these are 3 rows, A, B, C. I'm going to look at the single bit line, single bit, but a row is really 8 kilobytes. And this is just in one subarray. Assume that we had the primitive to concurrently activate these 3 rows, A, B, C. When you do concurrent activation in an ideal circuit, all of these share the charge at the same time, and the final value on the bit line is going to be charged if at least 2 of these are charged, and it's going to be discharged if at least 2 of these are discharged. That's the idea, based on charge sharing principles that are very fundamental. Of course, building this is a different thing, which we may talk about. But essentially, this is your final state. It's a bitwise majority function. And a bitwise majority is very nice. You could do a lot of things with a bitwise majority function. Now, imagine doing this function on 8 kilobytes at once, bitwise, and you have 1,000 subarrays in DRAM. That's 8 million bits at once, let's say. That's very high parallelism. Of course, you need to probably increase the power consumption in your DRAM chip. But computation does not come for free, right? We have power consumption in our processor chips. If you want to compute somewhere else, you cannot assume that power will not increase. I think this mindset, I'm pointing to a mindset issue because sometimes when you propose these ideas, people will say, oh, but this will increase the power consumption in DRAM. Well, yeah, it will increase the power consumption in DRAM, yes, because you're computing there. Okay, anyway, basically this is a majority function. You could do a lot with majority functions. You could actually translate your program to a majority function. There's actually very interesting work by Nani De Michele's group at EPFL that does logic synthesis using these majority functions that can be mapped to this substrate. But another realization is that clearly with Boolean algebra, you can rewrite this equation. You can set C to 1. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now you can do bitwise AND and bitwise OR. That's great. And you can expose it to the ISA with some function like this, bulk AND. The This is what we said. And actually, there are implementation issues that I'm not going to go into a lot of detail, but clearly you don't want to do this triple row activation in the entire DRAM subarray, because that requires very complicated row decoders. You really need 3 row decoders to be able to do that, but that's very expensive. So the way we proposed this is you create a special area in your DRAM subarray that are called designated rows. And if you want to do triple row activation, you move the data, row clone the data into those rows, and those rows are specially designated for doing triple row activation. So it's very simple, very low area cost, as opposed to building 3 row decoders. So if you want to do the bulk end of A and B, this is how you do it. You row clone A to one of the designated rows, you row clone row B to one of the designated rows, you row clone R0, which is all zeros, to designated rows. You do triple row activation, and the result is now in the bit lines, and you row clone the result into the destination row. That's the idea. So you need to do data movement, but data movement is constrained inside the DRAM chip, in this case, inside the same subarray actually. So this is much more efficient than doing moving the data all the way into the processor, especially if you have a lot of bitwise parallelism. Okay, so what are we missing? The question we asked was, we're missing actually a NOT, because once you have a NOT there, now you have a Boolean complete functionality. You can actually translate any program into a circuit that way, because an AND, not an AND, is universal, right? A NOR is also universal. It's Boolean complete. Of course, any program may not be efficiently translated, but you can translate any program into it. So we wanted to have the NOT. NOT is a bit harder, but the good thing is it actually kind of exists. You have the bit line, which stores the value that you read out of the cell. But the complement of the bit line, the other side of the sense amplifier, has the bit line bar, which is the complement or the NOT of the value. Now, what we did in this work is actually we fed that value into a special row in the same subarray, and that enables the NOT. You basically need to do, if you want to get the NOT, you actually have a special command that moves this to a special row. But you have that, you basically added a little bit more connectivity into the DRAM chip to get that complement value back inside the subarray. That's the idea. This is a little bit more cost. It's about 1% of the chip area in total, all of the modifications that we make. But this now enables your DRAM to be a general purpose, Boolean complete, bitwise computation engine. If you think creatively, you can really translate any algorithm into this. Of course, some algorithms are more amenable. I'm going to skip this, but basically these are the performance benefits. I'm going to summarize this. These are the energy benefits. They're much better than what you could do with traditional DDR3, 60x energy reduction, for example, here, and or NAND NOR. You can build any bitwise primitive on top of this clearly. And these are the summary numbers in terms of performance improvement and energy reduction.
Energy reduction compared to what?
Compared to this, basically the memory energy reduction. Compared to moving the data into a memory controller, and you assume that you have some end units in the memory controller.
Okay, so it's not to the full process.
No, it's not. Yeah, exactly. It's actually worse probably. The full processor is probably even worse. Yeah, exactly. But, yeah, we didn't want to overemphasize the energy reduction, and also we didn't have a great energy model for the entire system, so we constrained ourselves to doing the operations in the memory controller in this case. But if you look at the entire system, you'll get much better results.
Can I be provocative?
Could you say it again?
Can I be provocative?
Yes, please.
So how many applications can you do with this basic in the vector way?
Okay, I'm going to go to that next. Thank you. So this is the center of the world, basically. You can do any application. No, I'm just kidding.
No.
Basically, there are some applications that are good fit, like bitmap indices. If you're doing bitmap index-based databases, a lot of them operate on huge bitmaps, and they do ANDs and ORs, many ANDs and ORs actually. Of course, they do other stuff also, but they're dominated by these ANDs and ORs, and we do the other stuff in the memory controller. That's the idea, basically. And also, people have built some databases just to do these bitwise processing, because they wanted to take advantage of GPUs, for example. This bit viewing database from Jignesh Patel's group was built specifically for execution on the GPUs. So they wanted a lot of these bitwise operations, and that's a very good fit. Microsoft built this web search engine for the exact same reason, and that's also a very good fit. I think DNA sequence mapping is another example where we do a lot of bitwise operations, and encryption algorithms, which we're examining right now, are other examples. So clearly some applications already do it, but sometimes you need to rewrite your applications to take advantage of it. For other reasons also, people are rewriting applications. So I'm not going to claim that you can do all applications efficiently on this one, but I think once it's out there, maybe people will take advantage of it, right? This is very similar to GPUs. GPUs were out there, people were not using it, but once they become more programmable, people started using it, and people poured a lot of applications that perhaps many people didn't imagine could execute on GPUs before. Okay, so bitmapping, I'm going to skip some of these there in the papers, but essentially if you want to perform a query, you may, if you're using bitmap indices, you do many bitwise operations. And this is one example. You can store your data categorized in some way, and then you may have many bitmaps to represent your data, and the queries are basically bitwise operations across many rows in this case. So we actually looked at a bunch of different types of queries. This is one example over here. If you have a bitmap index database and if you query a bunch of users, a bunch of data over time, this is end-to-end query execution time. You get significant query latency reductions, 5 to 6x. This is end-to-end query latency reductions in this case. We don't have a good energy model, but we have good performance models to be able to get these results.
You the memory controller is the baseline, or now you're moving to the processor?
So in this case, we compare it to the processor, actually. Yes. If you do it in the memory controller, the reduction is a little bit less, certainly. Okay, this is we actually ported the bitweaving database that I mentioned that was developed for bitwise operations by Jignesh Patel's group, and again we see significant performance improvements in the queries that you can do with that database. And the other good news is as your data set size increases, your performance improvements increase. Of course, there's some saturation, but essentially you can parallelize a lot of these operations across the subarrays that you have in a memory module. And you can read more about this in this paper over here, which took 4 iterations to get published, by the way. It was rejected 4 times. I have a story later on at the end if we get to it about papers. So if you're writing papers,
Open that box.
I may open it later on. Depends on how much time we have later on. Okay. By the way, we actually, it's interesting that it took 4 iterations to get published, but we put it on archive before it was rejected once more. And other people built on this work and actually showed that you could do these operations in phase change memory, and they published it before this paper. And they were nice enough to actually reference our archive paper saying that they built on this work. Sometimes that also doesn't happen, right? That's okay, so the question is, does memory have to be dumb? And I don't believe that should be the case, and I think we need to build computing architectures with a minimal data moment. And I think thinking of memory as an accelerator that can do some operations really well is probably a good idea. And in this case, there were some operations that we thought memory could do really well. Now let me talk about a technology-driven way of thinking about processing in memory. And there's a lot of work going on in 3D stacked memory. You're doing some work in this area, for example, but I think there's a lot more to be done in this area going forward. And this is an opportunistic way of thinking about it. We have these 3D stacked memories that people are developing. Why not take advantage of them for processing? So basically, what is a 3D stacked memory? You have a logic layer that is tightly integrated with a memory layer through some sort of high density, high bandwidth interconnect, and also low latency interconnect, in this case through silicon vias in existing systems. But I think going forward, maybe there will be even finer grain interconnect that are going to be higher bandwidth, like monolithic 3D. Like the next project at Stanford, I think, has very simple vias that are much higher bandwidth. And I think those are very interesting works that can enable processing inside memory. And this is based on our RAM later paper. Even at the time when we wrote this, there were a bunch of 3D stacked memories. Okay, so when we first started looking into processing in memory in 3D stacked memory, we had several questions. I'm going to cover some of them in some detail. And we wanted to examine the maximum thing you can do with it as well as the minimum thing. So, and the first one is, what if we use this 3D stacked memory as a coarse grain accelerator? If we had the freedom to completely change the system, including the programming model, what kind of benefits would we get? If we had the freedom to change the system a little bit, just by offloading some functions, what kind of improvement we would get? I'm going to cover these, and I'm going to briefly talk about this minimal support. If we don't have much freedom to change the system, what is the minimal thing that we can do to get some benefit by pushing some computation into the logic layer? So I'll start with this one first, and by changing the entire system, because it's going to set the, I don't want to call it the upper bound because we really didn't optimize the system. I don't think it's really the upper bound. And later people actually improved what we've done and shown that you could get much better benefits. But I'm going to talk about the work that we've done. And when we first started looking at this, of course, it's important to be application specific because you're accelerating something and you want to put some function into the logic layer. And the key question is, what are you going to put over there? And at that time we were fascinated with graph processing. I think we're still fascinated by it because it's really employed in many, many things. Machine learning frameworks, bioinformatics, clearly all of these companies. And Facebook always doesn't like this number over here. They say that they now have 2.33 billion users. I don't know why, but somehow they keep getting users. That's why I put the circa 2015 over here so that I don't need to change this number over here. Again, scalable large-scale graph processing is challenging. If you throw cores at it, you don't get a lot of performance and actually waste a lot of energy. Why? Because a lot of the graph processing programs are actually bound by random memory accesses and relatively little computation surrounding those random memory accesses. So these are applications that are really exercising the energy bottleneck of memory access. Basically, you're doing very little computation, you're bringing all of that data into the chip, paying a lot of energy cost, and you're not reusing the data much. Of course, there are parts of the program that reuses the data, and those are actually a good fit for keeping it in the processor perhaps, but there's a good chunk where you should really keep inside memory. So this is the system we designed at that time. We wanted to put the entire graph processing functionality into the logic layer. And we wanted it to be scalable. As a result, we built essentially a parallel distributed system that can do it in memory. So in some sense, this is a lot of similarities to parallel systems that were proposed in the 1980s. For example, the J machine by Bill Daly. Except the big difference is you really do computation inside the memory here. So basically, you start with this logic and memory chips. If you look inside a chip, you have what's called the vaults. Vaults are essentially memory controllers that control the memory stack on top of them. And the chip is partitioned into some number of these vaults. They're connected with some network. Actually, network design for this is interesting, I think, also. That really determines how much computation you can ship between over here without getting bottlenecked. But basically, they're connected to each other. And normally, you have a DRAM controller. Over there, we put an in-order core, very simple in-order core, so that you don't make the thermal bottleneck worse. Because 3D stacking always has a thermal problem, and if you want to do computation inside there, you should be very cognizant of the thermal problems that you have. Okay, basically we put an in-order core over here. And this in-order core, whenever it needs to process some data, it basically moves the function to the data. It basically if the data resides on some other vault, it sends a function to that some other vault saying, vault, please execute this function on this data. So data doesn't move, but the operation that's to be performed in the data moves across the network. And of course, you don't want this to be restrained to a single chip. If you really want to have a large graph, you want to connect these 3D stacked logic and memory chips in some manner. Over here we had a Dragonfly network with which we connected many of these 3D stacked logic and memory chips. And now the problem becomes, of course, now that you're going out of the chip boundary, so you need to partition your data nicely such that whenever you want to move your computation to the data, you don't go off chip as much. Of course, it's not an easy problem, right? Graph partitioning. But other people actually have developed many mechanisms after this work that made the graph partitioning mechanisms better. And I believe there needs to be more work in that area. So the idea is basically you lay out your graph nodes on the chips first, hopefully with good locality inside there. And then inside the vaults, here the locality doesn't matter as much because you're inside the logic layer. But locality always helps. And whenever you want to do some action on a graph node, you send a message to the vault that houses that node. So this is really programmed by message passing in the end. We got rid of all of the coherence in the system, so it's not shared memory, it's all message passing. That's why I said that this is similar to the 1980s parallel systems. You had a question?
In this solution, the processors are almost not used in the end.
Almost what?
Almost not used.
Well, they're used to do the operations on the data, basically.
Yeah, but if you do a full graph traversal, then it will be each cluster will be used only once.
That's true. Yeah, that could be true. Yeah, if it's just a graph traversal without a lot of computation, but that's true for existing processors also. So there's no difference actually. That's why you're dominated by data movement in graph traversals today. At least we're doing it hopefully inside the memory and not moving everything to the core and back and core and back. So your point actually, I think, makes the case for graph processing in memory.
You still send the function, so it costs also.
Yes, but that's much less actually. So you're really exploiting the memory. You're not going off chip boundaries. That's why graph partitioning is really important actually in this case. That's why people have developed a lot of graph partitioning algorithms to improve the efficiency of this. Exactly, you will be bottlenecked by how many times you cross the boundaries of the chip. But today you're crossing all the time. That's why it's better than today. Okay, so essentially this is a message passing based system. You're doing remote function calls. And also it depends on how much computation you have. There are some graph processing algorithms where you do more computation than just graph traversal. And this is essentially what we have basically. This is your page rank, and we send a message. We have a programming interface, put versus get. It's very similar to distributed system programming. And we have non-blocking and blocking function calls. I'm not going to go through the details of the programming method, but you need new instructions to support these as well, clearly. Okay, I'm going to skip some of these function calls. And it turns out that if you do this, even the bandwidth is not used as much because you have a lot of bandwidth that's available to the processors. Then the processor can utilize the bandwidth because these are very simple processors, in-order processors. So to be able to utilize the bandwidth, we added prefetching mechanisms that exploit the message passing functionality as well as some locality in graph processing, which I'm not going to go through it. But I'm going to give you some results. It's a full system design, so it's impossible to cover it very quickly. You should really look at the paper. But basically, we compare this to 3 different systems. These are traditional systems, DDR3, hybrid memory cube with many core. For a fair comparison, we looked at simple in-order cores. But they're all bandwidth bottleneck, basically, because of the pin bottleneck, and you cannot increase the bandwidth significantly. Tesseract looks different because it doesn't have the processor-memory dichotomy, and it exposes a lot more memory bandwidth to the cores, 8 terabytes per second. And as a result, on average across 5 graph processing algorithms, it improves performance significantly. Essentially, without prefetching, you get about 9x performance improvement compared to DDR3, and with prefetching, you get about 14x. We didn't really optimize the system. I believe you can actually get more, maybe 30x and 40x, 50x. Actually, other works that built on this showed even more performance improvements than we have shown. So I think it's good news that there's more to be done. But of course, there's a limit at some point, right? Even if you specialize for graph processing. By the way, this is not I believe it's a general purpose substrate. Even though we evaluate on graph processing, these are general purpose cores. You can offload any type of workload on it. Maybe some machine learning workloads would be good to offload as well. So some of the benefit is basically we are able to exploit 2.9 terabytes per second of that 8 terabytes per second. I believe there is more potential because of this picture over here. If you look at DDR3, existing systems exploit 80 out of 104. We're exploiting 2.9 out of 8 terabytes per second. Basically, our efficiency is much lower in terms of the fractional bandwidth that we exploit. I believe by redesigning the algorithms better, you can exploit even more. Okay, we have a lot of analysis in the paper. What fraction of the benefits is just coming from additional bandwidth that you provide without changing the programming model. Some of the benefit can be obtained that way, but not all of it. A lot of the benefit is really coming from the programming model, but you can read the paper for those details. So essentially, the benefit is not just coming from the fact that you're adding more bandwidth. A lot of it is coming from the orchestration of the messages in the system. Okay, energy reduction is also significant. This doesn't even include the cores energy over here in the baseline because the baseline cores were a bit heavyweight and we don't want to include them. So you get about 8x energy reduction average across those graph processing algorithms. If you're interested, the paper is over here. But you can also read the works that are built on it. There are a bunch of works. I believe they'll be coming up in the future conferences also. Okay, so that was basically changing the entire system. We get rid of coherence. We get rid of actually we get rid of virtual memory in this case also because everything is physical memory. You can think of this as a primitive GPU. It's like a GPU. Offload everything to a GPU and forget about it. But of course, over time, you need to make it more programmable. Maybe average Joe is not the person to program this. Okay, then we actually wanted to look at how do we actually get benefits from simple function offloading. So we did some works that I'm not going to talk about, but I'm going to focus on a more recent work that we've done collaboratively with Google. And I already mentioned this a little bit. Basically, we studied the workloads that are executed on consumer devices for 1.5 years or so. And we wanted to understand, essentially, where the energy goes in these devices and these important workloads. And these are the workloads that we studied. And they're very interesting, I think. Equivalents exist, of course, in non-Google domains as well. And we wanted to quantify the energy cost of data moment. I've already given you this data point. We basically found out that more than 60% of the total system energy is spent on data moment. And we wanted to examine one solution to the data moment problem, moving computation close to data. And the challenge here is, of course, even more limited energy and area budget that you have in these consumer devices. So we were very cognizant of this, and the paper has more detail on that one. So the second key observation that we had was a significant fraction of the data moment often comes from simple functions across these different workloads. And we basically are able to design lightweight logic to implement these simple functions in the logic layer. And we looked at two different solutions, basically small embedded low power cores and small fixed function accelerators. So you can ship that function, offload that function to either this one or more specialized function executor over here. In my opinion, the logic layer is best kept reconfigurable so that you could actually instantiate the functions that you want in the logic layer, maybe even dynamically sometimes. So we found out that basically the performance and energy gains are significant. So the translation of this is basically similar to the other results. You basically improve performance by about 2x and improve energy by 2x. So it's not like the 13x or 8x that we've seen before. It's about 2x if you do it carefully.
Sorry.
Yes?
What kind of benchmarks are you using for that? Because we saw much more significant improvements.
Yeah.
So what exactly are you to PIM accelerator?
I'm going to show you examples. Yeah, no, that's okay. yeah, sure. That's not the end. So basically, this is what we did. I'm going to skip this. But basically, these are the workloads. Web browser, TensorFlow, video playback, and video capture.
For the streaming applications, I would expect a much higher performance improvement. For the web browser, I agree, it's a pointer chasing function, then it's a parser. Yeah. So,
but streaming applications also have prefetchers, and performance is actually pretty good if you do good prefetching into the processor. Yeah, caches are not effective, that's right, yes, but prefetchers are very effective, right?
Probably energy should be much more than a factor of 2.
Yeah, but that's what we saw with our energy model. I mean, I agree that other even higher benefits are possible. But we tried to model a lot of detail over here. And
that's interesting. I'll have to look at the paper.
Yeah, sure. Please take a look. Yeah. But I think being conservative is better than being...
Absolutely.
Yeah.
But I don't know.
Yeah. So I'm going to show you some results, basically. So this is TensorFlow Mobile, for example. I picked this one. I think browser is very, very interesting also, actually. But basically, this is machine learning framework that's used. It's used for inference in these devices that are small. And we found out that more than 50% of the inference energy is spent on data movement across 4 major networks that we examined. Some of these are very deep networks at the time. And more than 50% of the data movement comes from very simple functions like packing, unpacking, and quantization. These don't require much computation. They're bottlenecked by data moment, but you're going through the processor to be able to do that. So what is packing? Essentially, across the layers of the network, you reorganize the data to be more efficient in the processing. You reorganize the elements of the matrices, and you pack it in some other form. And there are some results in the paper that you can look more detail. But this is the takeaways is it's a simple data reorganization process that requires very simple arithmetic. So it's a very good fit for processing near memory or inside memory. Quantization is another example. Actually, all of the neural network inference engines do quantization. They take the values, they quantize them into much smaller values, and they operate on them to reduce execution time and energy consumption. And we found out that a significant fraction of the inference energy comes from, and execution time comes from quantization only, and most of the quantization energy comes from data movement. And again, this is a very simple conversion operation that requires shift, addition, and multiplication. That's it. You just need to add these functions into your in-memory unit. And essentially that's what we did basically. These are good candidates for PIM execution. And we went through the applications to find out what are these interesting things. And we built a very detailed simulation engine for these workloads and Chromebook type of systems. And this is the normalized energy results that we get. And these are, you can see that these are some of the functions that I didn't talk about. Packing and quantization are here. In Chrome browser you have different types of, we look at page loading and tab switching, for example, and you do different things like compression and decompression are very important when you're doing tab switching. But of course, compression and decompression are very general functions that could be used by other applications also. And these are the energy reduction that we saw. It's compared to CPU only. If you have a general purpose core, simple core and PIM, you get significant energy reduction, but accelerators actually improve the energy even more. Specialized fixed function accelerators, yes.
I'm bothering you, but it's very interesting. How did you change the software?
So software changes were actually minimal in this case. We basically, maybe that's where the energy, that's why the performance improvements are not as large, but basically we delineated the functions that need to be shipped.
So it's manual?
It's manual, yeah, it's manual. We didn't do any compiler or anything over here.
Compiler, can you get the code? Can I get the code?
Let's talk about it afterwards.
Okay.
Yeah. Okay. Sure. It's not open source because it was done with Google, but
that's the problem. But
we could potentially share it with you.
Have the compiler, and I would be curious because to compare results.
Okay.
Because there's all this management of not only programming the function but also sending what to do.
Yeah, absolutely, absolutely. I agree. Yeah, and I think we didn't really fully optimize everything. Okay. We wanted to. Our purpose was a bit different, and we wanted to care about the Okay. Essentially, you get significant performance improvement, and I'm not going to go through the details. There's a lot of analysis in the paper of these functions if you're interested. Okay. And performance improvements are also commensurate, but sometimes if you have a general purpose core, you don't get a lot of performance improvement. You actually need to specialize what you have in memory. And again, performance improvements are this execution time. Execution time reduces by about 2x. You basically halve the execution time, sorry. And there's more detail in the paper that I'm not going to talk about right now. Okay. So we actually, I don't have time to discuss all of these, but we've been looking at doing similar things in the GPU. For example, if you have a main GPU that's very capable, and you may have simpler GPUs in the logic layer, how do you distribute the work across them? And we wanted to be programmer transparent. If you're programmer transparent, we don't see a lot of benefits, but you still see some benefit over here. And we have some other works that I'm not going to talk about. I'm just going to flash them, and these slides will be available. We looked at accelerating pointer chasing in 3D stacked memory. If you want to build a specialized accelerator for pointer chasing, what kind of benefits you would get, how do you design the accelerator? These are hardest programs, of course, because you chase pointers. But the latency benefits and also the energy benefits of not moving data to the processor actually buy you a lot of performance over here. And we looked at doing that also without any programmer support. And again, you get performance improvements. And we did it in the memory controller solely, not necessarily in the logic layer. This also buys you some performance, but at a lot of complexity. Okay, let me talk about this one a little bit, because this transitions us to the adoption issues also. So these are all good, but they're also changing things significantly, unless you build a compiler infrastructure that enables you to do this automatically, of course, right? I think that's very important to do. We also wanted to ask the question early on, like, what is the minimal thing that you can do without changing things significantly? So all of these actually assume that you have some virtual memory infrastructure, well, at least a simple function offloading assumes that you have some virtual memory infrastructure on the memory side, which is really hairy. I think virtual memory is one of the hairiest problems that we have whenever we want to ship something somewhere. That's true for GPUs. That's even more true for near data accelerators. Coherence is another one. That's also there are two very hairy problems that we have, and they need to be solved. And we wanted to really ignore those problems and keep it exactly the same. So with minimal change to system and programming, how can we take advantage of 3D stacking? And the idea is PIM-enabled instructions. I'm going to just give you the ideas over here. Ideas are very simple. As I said, we want minimal cost, minimal change to the system, no changes to the programming model, as little change as possible to the coherence, and no changes to virtual memory. And the idea is very simple. As I said, you expose each processing in memory operations as a cache-coherent, virtually addressed host processor instruction called a PIM-enabled instruction that operates on a single cache block. This also gets rid of the data mapping problem because single cache block resides on a single memory module. You don't need to map your data into the same memory module because it's already there. So it actually solves a lot of the problems. Of course, it's very restricted also. So for example, you have a PIM-add primitive that the programmer uses or the compiler generates, and this could be executed either in the processor or in memory. And if it's executed in memory, processor does the address translation before shipping it to memory. Processor acquires the coherence permissions before shipping it to memory. So processor is already doing all of that anyway. We're piggybacking on that. And it's on an instruction level. You're not shipping multiple functions, so you don't need to solve the multi-cache line coherence problem or multiple address translation problem that you may have with multiple instructions. Every instruction, on an instruction basis, you decide whether to ship or whether to execute in the processor. So clearly, this requires no changes to the sequential programming model, no changes to virtual memory, very little change to cache coherence because you need to lock the cache block that you're operating on, which already exists in processors, but you need to actually do it. And there's no need for data mapping, as I said. We also had a second key idea, which is figuring out where to execute this. Of course, if you have an instruction that's enabled with PIM, you need to have a decision mechanism to decide where to execute it. And we have a mechanism that predicts, based on simple locality metrics, where to execute things. I'm not going to go through this in detail. But this is an important mechanism because you don't want to always execute in memory. You don't want to always execute in the processor. You really need to decide. Okay, so basically, the key idea is this. This is, again, based on graph processing. We actually tested with more applications. But if you look at this particular code, you need to bring in a 64-byte cache line, and you need to write back a 64-byte cache line. So you basically transfer 128 bytes. If you actually translate that to a PIM-add like this, and if it's executed in the main memory, you just need to send the value, and hopefully you send only 8 bytes, if your interface allows you to do that. Okay, so executing always in memory, not a good idea, of course. You go and figure out where are the opportunities. We manually did that again. And you decide to execute all of those PIM adds or whatever instructions that you have, always in memory. Some applications gain a lot, some applications lose a lot. Why? Caches are very effective over here. And here you don't have graphs that are fitting in the caches. So basically you need to have a decision mechanism. So this is an example, and we actually add some fences which are similar to, because you may actually send a lot of PIM adds to memory. You need to somehow synchronize your operations in the processor, and we added fence operations to ensure that all of the PIM-enabled instructions are done before you move to the next instruction. It's very similar to memory fences that we have today. And these are some of the instructions that we imagined based on our analysis of the programs at the time. For example, you have 8-byte integer min, floating point add, hash table probing, histogram bin index, Euclidean distance computation for streaming cluster analysis, stream cluster benchmark. And you can see that input can be anywhere from whatever, 64 bytes, 4 bytes, dot product also, right, for support vector machines. So this is very dependent on the application. That's why I believe having a reconfigurable engine at the logic layer is a very good idea, because you can instantiate these instructions nicely. Because in the end, the instructions that you want are going to be very application dependent, I think. Okay, I already said all of this, and there's a lot more in the paper. So the key to practicality is this single cache block restriction. Basically, each PIM-enabled instruction can access at most one level cache block, and similar restrictions exist in atomic instructions, so that you can actually ensure the cache coherence. Of course, there are many benefits to this. Like one memory module, cache coherence and virtual memory is interesting and easy, and locality monitoring is easy also. But of course there's a downside to it also, because you can only operate on a single cache block whenever you ship something to memory, right? You cannot do what we discussed earlier, operating on 8 kilobytes or 8 million bytes at the same time, right? So we did evaluations with 10 different data intensive workloads. You can see the domains: graph processing, in-memory data analytics, machine learning, and data mining. And we looked at multiple different input sets. And on average, we saw that with large input data sets, you can improve performance by about 47%. So this is nowhere near the 13, 14x that we discussed, but we were changing very little in the system. Okay, let me give you some examples. So this is with large input sets, for example. And these are different workloads over here, this geometric mean. If you execute always these PIM-enabled instructions that we put into the program, always inside processing in memory, you get this much performance. If you're locality aware with our decision mechanism, you get more performance. But sometimes our locality aware mechanism is not good, as you can see. So there's room for improvement. But on average, you do better. And you can see the paper for more detail. So if you have small inputs, that fit into caches. So these are the cases where caches are very beneficial, as you can see. If you ship things to memory, you lose performance a lot. There are some cases where you don't. But if you actually have a decision mechanism that can decide to execute in processor when it makes sense and to execute in memory when it makes sense, you actually improve performance even in these simple, small input data set workloads. And medium ones are even more interesting. Basically, in this case, you sometimes lose, sometimes not gain if you always ship to memory, sometimes gain a lot. If you have a decision mechanism, you get better than both of the mechanisms. But our decision mechanisms are not optimized, as you can see. Sometimes we lose compared to PIM only. So there's room for improvement for intelligent decision mechanisms in terms of when to ship, what to ship. Okay, and these are the energy results. The big energy benefits come from medium input sets and also large input sets over here. That's where you gain a lot of energy. But you don't gain a lot of energy if your input sets are small. Okay, so clearly this has some advantages and disadvantages. I think adoption-wise it's nice because it's simple and low cost. There are no changes to programming model and virtual memory. And we also, on top of this, dynamically decide where to execute an instruction. The disadvantages are clearly this doesn't take full advantage of the PIM potential, but probably takes a step getting us to the PIM potential. And I think single cache block restriction is limiting. And finding out solutions to this problem is important. Okay, so we actually have a similar paper on GPUs, but I'm not going to talk about that. So here, this is not automatic. This is manual, but we want to do it automatically over here. So we did some compiler paths on GPUs to transparently offload to simpler GPUs in logic layer. You get similar performance benefits, 30 to 50%. And I already said this, and I'm going to skip some of these. So coherence is an issue, actually. This is a paper that was published at ISCA very recently that I may talk about later on. Okay, but basically we have a big challenge. How do we enable these processing in memory systems, which means that how to make computing architectures more data-centric and fundamentally energy efficient. And I think that's also important for high performance, as we've seen with these results. And I think all of this comes with minimal data movement. I think actually developing interconnects that are much more energy efficient is also very important, but I think we don't know how to do those yet. If we can somehow figure out how to develop extremely efficient interconnects, we can put memory and computing much closer together, but we'll see if that can be developed. Okay, so let me talk about adoption a little bit, because whenever you have new technology, it's really important to think about adoption. It's not clear if it can be successful without thinking about the software. You mentioned the average programmer Joe, for example. But even expert programmer Joe may not be able to take advantage of new technology if it's not posed well. And there are clearly a bunch of adoption issues for processing in memory. Starting from software, functionality, applications, how do you build the software for PIM? How do you program it? What are the interfaces? What is the support provided by the compiler and the hardware for those models? What is the system support for coherence and virtual memory, so that you can get the large benefits? And what is the runtime support and compilation support for adaptive scheduling, data mapping, and access and sharing control? And also good infrastructure to assess benefits and feasibility. I don't have answers to any of these fully, actually, but I think these are things that we need to solve collectively. And I believe all can be solved with a change of mindset. I think we also have a mindset problem, plus a lot of business problems in memory. Sometimes people are slow to change, right? Sometimes, okay, all the time, maybe. Yeah. But we need to revisit the entire stack. We'll talk about the mindset problem if we have time in the last point that I have. But I think we can get there step by step. So we recently written this paper, this invited paper that talks about a lot of the open problems in the area. If you're interested, you can take a look and provide feedback. So what are the key challenges? I think code mapping, where to execute code, is a key challenge, clearly. If you're adding A plus B and storing the result into C, it doesn't help if A is here, B is here, and C is here. Clearly, you have a problem. You need to map the data into the same memory stack to be able to operate on it locally. Otherwise, you might as well bring it into the main processor. Data mapping is also, well, that was data mapping actually. What I described is data mapping, but code mapping is whether you execute it here or here. That's also important. How to do it? So this is I mean, this doesn't answer all of the questions, of course, but this is one step toward the problem. But there's a lot more to do. How do you schedule the code? There's more. Coherence is a big problem. This is based on the paper that we've written recently that was presented at ISCA. Basically, if you partition the code such that some of it executes on the processor, some of it executes on a near data accelerator, processing in memory, using the traditional coherence mechanism, fine-grained like MESI-like, Moesi-like coherence, or coarse-grained coherence, coarse-grained locking, or non-cacheable approaches to coherence, which is you don't cache things in the processor, they're not good basically. Actually, fine-grained coherence seems to be the best across what we've seen. With non-cacheable, you lose a lot of performance. This is geometric mean. So we've looked at in-memory databases and graph processing, as you can see over here, and we partitioned the programs across the CPU and memory in a relatively fine-grained manner. It's function offloading again. But coherence becomes a bottleneck in this case. And you don't get if you eliminate all of the coherence bottlenecks, this is ideal PIM, you get significant performance improvement, 50% in this case, but actually these are smaller data sets. With larger data sets, we see a lot more benefits. Maybe some of the differences that we see are based on the data set. Because in the paper, we report also results with larger data sets, and we see 8x, for example, 8x, 9x. But sometimes it's easier to do the simulations with smaller data sets, as you know. So basically, traditional coherence mechanisms don't do too well. We need different coherence mechanisms, and lazy PIM is one example of this, and you can read about it in this case. We renamed it to Conda after 4 rejections or something like that. So it turned out coherence for not near data accelerators was better. But essentially, it's the same idea as lazy PIM. The idea is very simple, actually. Well, I think the complexity is high. I will admit that. But the idea is very simple. You ship code to a near data accelerator, processing in memory. And in processing in memory, you keep track of which cache blocks you touched. And you keep signatures for it. And once you're done, you check whether the CPU overlapped with those signatures. It's very similar to transactional approaches. It's a bit simpler because CPU never rolls back. It's not full transactional memory. You only roll back the processing in memory engine. And of course, there are challenges to minimize data movement in this case. Transactional memory makes different trade-offs because transactional memory is employed actually within a chip usually. Okay, how to support virtual memory? I think this is something that really needs a lot of attention. Actually, virtual memory needs to be completely rethought, in my opinion, going forward with different memory technologies. But this is a very hairy issue. And we made an attempt over here. There is some solution over here, but I don't think this is a very general purpose solution. How do you design data structures for processing in memory? I think this is also important. Once you actually have processing in memory, your data structures maybe should not remain the same way. Because if you have parallel data structures in your CPUs, you can actually overlap a lot of the latencies that you have in memory. But if you don't have parallel data structures in your memory, then you lose a lot of the performance benefits of processing in memory. So you really need to think parallel also inside the memory. And simulation infrastructures for PIM. Actually, we released our infrastructure for processing in memory, Remulator PIM. You can find it online right now. We released it very recently in June. We'd be happy to get bug reports. Remulator is very heavily used in industry as well as academia, and we work closely with companies that send us bug reports for Remulator, and we extend it for PIM. So we'd be happy to get bug reports also. And I think we're working on FPGA-based infrastructure, extending the soft MC infrastructure that I mentioned as well. And I think simulation infrastructure for processing in SSDs is also important, and we have some work going on. We have this infrastructure that can do realistic studies of SSD devices. It's called MQSIM, multi-QSIM. We're extending it for processing inside the SSD device. The SSD devices are actually very sophisticated because they have DRAM inside also. You could do processing inside the DRAM as well as the processing inside the flash over there. And clearly, new application and use cases for PIM are always important. That's why we've been looking. Well, that's not why we've been looking at bioinformatics, but to enable some of these applications, processing in memory is very useful, and that's why we've been studying some of these applications. I'm not going to talk about this actually because we don't have time, but there's a lot more to do in this area. Okay. So I think I'm almost done with this particular part of the talk. Let me conclude. I believe we have a big memory problem, and it's time to design principled system architectures to solve the memory problem, and for that we need to be data-centric. And I think we're violating a very important system design principle. In every system that, in computing system courses at least that I've seen, balanced system design is a key principle, right? But fundamentally, the systems we design are completely imbalanced. Right? The data resides in this place, processing is done in this place, and fundamentally we're violating that balanced system design principle at the very beginning of the system design. It's a bit sad, since we teach balanced system design as a principle and we violate it in the first step. But maybe we need to rethink how we violate it, and how maybe we should not violate it to begin with. And I think this requires enabling computation capability inside and close to memory and other parts of the system that have data. And I think this can lead to orders of magnitude improvements. I've given you some examples. There's more. Enable new applications and computing platforms that are heavily bottlenecked by the memory today. And I believe it can enable a better understanding of nature as well, because I don't think nature is doing processing in only one place. And maybe other things that we cannot imagine right now. So I think the future is actually bright. There are a lot of challenges in underlying technology and overlying problems and requirements, but if we think across the stack and design enabling systems, we can overcome them. But I think we should really be cognizant of the adoption issues. That's really important. So whenever I conclude the processing in memory talk, I usually talk about positive examples. If I have to name one memory technology that has revolutionized our lives recently, what would that be? Flash, exactly, yeah. This thing that I have over there. I would not have a cell phone in the form it's today if I didn't have SSDs or flash memory, right? But it was a very doubtful emerging technology for decades and decades, right? Actually, people who designed this initially were not valued as much, maybe. And people who were working on garbage collection algorithms for flash memory, they were kicked out of NSF. They were not given funding, because who cared about this technology, right? But we know today better, hopefully, and we should know going forward better not to dismiss some of these technologies, I think. So clearly these technologies are there and they've revolutionized our lives, and we're able to write a lot of things about them, and these are actually infrastructures that have enabled these technologies. So there's a lot more work to be done. And I think there's a lot more work to be done over here also, but we need to do it. Okay. I think that concludes the computation and memory part.